Here in Module 2.1, we're taking a look at polynomial functions. Actually, our first look at polynomial functions for this semester. And we will consider polynomial functions and extensions of polynomial functions for at least a couple of modules here. They are really important and useful in a lot of practical applications of business in particular, plus calculus. In calculus, you'll use polynomial functions very frequently. Polynomial functions and their derivatives come up a lot in calculus. So let's just start. Let's begin at the beginning here on recognizing how do we recognize what is a polynomial function. And from your reading, you know that a polynomial function basically is just a string of powers of x added or subtracted together. So, or it doesn't have to be the variable x, it could be the variable t, or t for time, or any other variable, but the input variable, which we usually use x, so I'll just say x for now. The input variable x to a whole number power, and several of those terms, x to a number power, added or subtracted together is basically what we mean by a polynomial function. And then a specific case of a polynomial function is when we just have one term of x to some whole number power, which is the case here in part A with f of x equals x to the 7th power. And in the case where we just have a single term raised to a whole number power, we call that a power function. And that is the answer to part A, where we're identifying either power functions, polynomial functions, or if the function fits neither a power function or a polynomial function definition. So this is a perfect example of a power function in part A. Part B has f of t, and it doesn't matter that we changed the variable name. Now we're just using t instead of x, which is fine. We've got f of t equals t cubed to the 4th power. And we see that we have a single term raised to not 1 power but 2 powers. But we know from our exponent rules that a power to a power can be simplified. And we can multiply. Getting f of t simplifies to just t to the 12th power, which is the variable raised to a whole number power, and so part B gives us another example of a power function. In part C, we've got more than one term. We've got g of x equals x squared minus x cubed. Each term is a power of x, a whole number power of x, and we are either adding or subtracting those terms together. That is a classic example then of a polynomial function. In part D, we've got h of v, where v is the input variable. H of v equals v cubed over v to the 4th minus 3. All of the terms here are either just numbers, which are fine, or whole number powers of the variable, in this case v. So if we've got nothing but whole number powers of the variable, then it at first might look like this is a polynomial function, but those powers of the variable, in particular v cubed and v to the 4th here, a polynomial has to combine those terms by simply adding or subtracting them together like we saw in part C. In part D, we've got division of v cubed by v to the 4th minus 3. That division, and especially dividing by the variable, dividing by that v to the 4th term, means that we do not have a polynomial function. It's not just a sum or difference of whole number powers of the variable. This is not a polynomial function, and it's not a power function, certainly, because it's not just the variable to a whole number power. This is neither, though it is a type of function that we deal with frequently and that we will see in future future modules, that's the word I was looking for, future modules in this semester, a quotient, a division of polynomials is called a rational function. For the purposes of this example, we'll simply answer that it's neither a polynomial nor a power function. In part E, we've got g of s equals 3s times s plus 4 times s plus 2 times s minus 3 cubed. And here we have whole number powers of my variable s, but we're not simply adding or subtracting them together, we're multiplying them. So then we might suspect that this is not a polynomial function, because polynomial functions are defined as simply a sum or difference, not a product of whole number powers of s. But we saw in part B, way up in part B of this example, that we can use our operations sometimes to simplify the expression we're given and work it out so that it actually does fit our definition. And that is the case here in part E as well. We know that, for example, let me pick on s plus 4 and s plus 2. If I were to multiply s plus 4 times s plus 2, FOIL that out, then I would get a sum of terms if I actually work out the multiplication. And that's the idea here. If we were to actually work out not just that multiplication, but also the times 3s and also the times s minus 3 cubed, well, first of all, that's a lot of multiplication to work out. Second of all, I'm not saying that you have to work out all of the multiplication, but if we can at least recognize that all of that multiplication can be worked, we can FOIL all of these factors out. And if we do so, FOIL it all out and combine like terms, then what we would have is a sum or difference of a bunch of powers of the variable. What I'm showing now is that I didn't multiply everything out, but I did go ahead and do all the first times first so that I can see, and you don't even have to go this far. As long as you recognize that you can multiply it all out, that you would get whole number powers of the variable, then you're good. Just to illustrate my point a little bit here, if we multiply 3s times another s times another s times s cubed, we would get 3s to the 6th power. And then a lot of other multiplying and distributing, a lot of FOILing, a lot of terms that I'm including here in this ... that we don't need to work out, but what I'm saying is we've got a whole number power of s plus another whole number power of s plus another whole number power of s, and finally I went ahead and worked out the last times last term of all of these factors, and I would have minus 648s. I don't need any of those particular terms, but I could multiply it all out and find all the whole number powers of s that I'm adding or subtracting together and see that in fact it is a polynomial function if we do all the multiplication. Finally, in part F, we've got p of u equals 4 to the u plus 3 power. And this, again, at first glance here, looks like, we've got a variable, we've got a whole number power. It looks like it might be either a polynomial function or a power function. Since we've just got the one term, maybe it's a power function. But no, here we have to be careful. All of the examples in parts A through E that we've seen so far have something in common, that they all have the variable to a number power. This is different. Part F has a number to a variable power. That's a little change in the notation that makes a big change in the behavior of the function and the type of function we're looking at. neither a power function nor a polynomial function has a number raised to a variable power. That's not how we define power or polynomial functions. It's always a variable to a number power. So in this instance, we have neither a power function nor a polynomial function, but this is a very important type of function. A number raised to a variable power is a type of function that we'll study a little bit later this semester called an exponential function. And those are crucial to working applications of exponential growth. And in business, things like compound interest and investments, mortgages, lots of money problems that involve interest, basically any money problem that involves interest and compounding interest, then leads to an exponential function, and we need to know how to work with those. We'll get to those later on this semester.